So in our previous videos, we have seen how light, which for many years was thought of as strictly a wave phenomenon, actually can exhibit particle behavior. We're going to see if the same thing is true of matter. That is, will particles, like electrons, exhibit wave behavior? The definitive experiment that demonstrated the wave nature of light was the double slit experiment. If you recall, this was the experiment where a light beam is shown through two slits, and the light going through the different slits forms an interference pattern at a distant screen. This is something that only happens with waves. Particles don't form those interference patterns of bright and dark fringes. So what would happen if we took electrons and had them go through a series of slits, double slits? Here you see a setup where I have two slits represented by the openings there, the gaps, and then I have some electrons which are being accelerated by a potential difference, and they are going through various slits. And they get something over here which doesn't look like much of a pattern. Let's see what it would look like when we did a lot more electrons going through. Here is what the pattern would look like after 100 electrons. And then after 3,000 electrons have gone through and recorded their presence on the photographic plate, perhaps that's it, at where the screen would be, you start to see a little bit more of a pattern. You can almost see a pattern emerging here. Now here are 70,000 electrons having gone through the two slits. And although the electrons are going through just one or two at a time, when you have many electrons going through, you do see the formation of an interference pattern. You see fringes where there's a lot of electrons that are hitting at a certain point, and then you see places where very, very few electrons are hitting. And so it turns out that electrons interfere with each other just like waves do. It's also important to notice that if we covered up one slit, this wave-like behavior would go away. We would see simply what we would expect to see if electrons were not exhibiting any wave behavior. They were simply going through the slit, and they piled up behind the slits. So, as it turns out, particles like electrons can exhibit wave-like behavior in some experiments. The wavelength of these waves was derived by a physicist by the name of Louis de Broglie. I consider him perhaps one of the luckiest physicists of all time. He was a descendant of French nobility. His nickname was Prince Louis. And for his doctoral dissertation, he actually came up with this formula. And you will recognize the formula that you see it here as a simple inversion of the formula that we saw already, where we said that the momentum of a photon is Planck's constant divided by the wavelength of the photon. Well, if that's true, then perhaps the wavelength of these matter waves, these electron waves, would be given by Planck's constant divided by their momentum. And if you work it out, the frequency of the waves would be given by the energy of the electron divided by Planck's constant. Now, when he submitted this for his doctoral dissertation, his doctoral committee wasn't quite sure what to do with it. They didn't know if it made any sense. And so they sent it on to Einstein, him being the most respected physics expert in the world at the time. And he said, yes, it looks like it makes sense. And so, of course, this trivializes his contribution, but one could almost say that he got his doctorate and the Nobel Prize, by the way, by simply inverting a formula that had already been known. Now, the original verification of the wave behavior of electrons was not made using a double slit experiment. It was accidental discovery in this so-called Davison-Germer experiment. In this experiment, an electron beam was fired at a nickel target, and when they detected the electrons after they bounce off the nuclear target, they found that they formed an interference pattern that you would get like if you had taken a light beam and shined it on a crystal. So this is another verification that particles like electrons can exhibit wave behavior. So on this slide and on the next two slides, I will discuss some of the questions surrounding quantum mechanics. This isn't part of the AP curriculum even in a normal year, so if you want to skip ahead to the questions after these next two slides, that's fine. So the double slit experiment illustrates some of the more peculiar features of quantum mechanics. Let's run the experiment again, but this time we're going to put an electron detector near one of the slits. Now, this detector doesn't slow down or change the trajectory of the electrons in any way, but it does allow us to tell which slit a given electron goes through. What do you suppose the pattern would look like if you let electrons go through with a detector in place? Now, I don't have a slide that shows this, but it turns out that you would not get an interference pattern. It would look as if the electrons were particles. That is to say, you'd see a clump of electrons behind each slit. So what's really going on here? The answer is that no one knows. Or perhaps it is closer to the truth to say that there are many different ideas about what's going on, but since each of the ideas agrees with all the observations, trying to say which one is the reality may not even be a scientific question. One of the ideas is known as the Copenhagen interpretation. This was, and with modifications remains, the most commonly accepted interpretation of quantum mechanics. Or perhaps you should say it is the second most commonly accepted interpretation of quantum mechanics behind the non-interpretation interpretation, which says that we know how to get the answer. Who cares what it means? Just shut up and calculate. In the Copenhagen interpretation of the experiment, the electrons do not have a defined position or momentum as they go through the slits. The state of the system is described by a superposition of possible states known as a wave function. Now, the evolution of a wave function is completely deterministic. That is to say, the behavior is completely predicted by what came before. When the system is observed, though, the wave function collapses. That is to say, it assumes a particular value of all the possible values that it could assume. And the value that it assumes is random. The probability of assuming a certain value, for example, say finding the electron at a certain place on the screen, is determined by the wave function. At the screen, wave interference will result in some of the places having a high probability of finding an electron and other places with zero probability. So if we observe the electrons at the screen, the electrons exhibit our expected wave interference pattern. However, if we put a detector at one of the slits, the wave function collapses before the interference takes place. So there is no interference pattern at the screen. Now, much discussion has taken place over the years about what is meant by observation and what does it mean to collapse the wave function. Regarding observation, for example, is there something special about an observer? Can the observer be a machine? After all, the machine is also a physical system, so presumably it too will exist in a superposition of quantum states. How then will this larger quantum mechanical system collapse its own wave function? Such considerations led some to speculate on a special role for consciousness in quantum mechanics. It is postulated that consciousness is something apart from the physical universe, and so therefore can collapse the wave function of the physical system. But that debate is more philosophical than strictly scientific in nature. Another feature of the Copenhagen interpretation that's often discussed is this idea of collapsing the wave function. We know now that there are ways to do the experiment so that the decision to observe which slit the electron goes through can be done after the fact. This is called a delayed choice experiment. So, if we make the choice after, perhaps long after the electrons have passed through the slits, does the collapse of the wave function when we observe which slit the electron went through? Does that collapse of the wave function travel backwards in time? It is considerations like this that have led some physicists to interpret the collapse of the wave function not as a change in a physical system itself, but as in a change in our information about it. Now, you can take this pretty far. There are even some who suggest that the information itself is the only real thing in the universe. Our reality, according to these theorists, is constructed from information. It from bit, as John Wheeler called it. Another idea about quantum mechanics is the many worlds hypothesis. To vastly oversimplify, the answer to the question, through which slit did the electron travel, is answered by saying it traveled through both. In this interpretation, there are many different realities. In some of them, the electron went through the upper slit, and in some of the other realities, the electron went through the lower slit. Now, these realities can interfere with each other, making the interference pattern happen at the screen. But when we make an observation, that interference ceases. But it's not a wave function collapse because both states continue to exist, albeit in different universes. And there are many other different interpretations of quantum mechanics as well, such as the pilot wave theory, or Richard Feynman's sum over all the possible paths the electron could have taken. The bottom line is that all the main theories yield identical predictions. And so it often boils down to which kind of weirdness you are prepared to accept. Now, the thing that the AP curriculum would want you to know about all this is just that at quantum scales, you have to treat particles as having a wave-like nature as well. And in fact, the motion of a particle is described by a wave function. This means the particle no longer has a definite position and momentum until it's observed. Now, what does the wave function then represent? What is waving, if you will? Well, the wave function is commonly described as a probability wave. In other words, the intensity of the wave at any given point, actually the intensity squared, indicates the probability of detecting the particle at that certain position. Now, the fact that a particle is described by a wave function, meaning it can, when measured, take on a range of possible positions and momentum, means that there is a relationship between the spread in possible positions and the spread in possible momenta. This is known as the Heisenberg uncertainty principle. Here are some videos that you can look at your leisure that describe the Heisenberg uncertainty principle in greater detail. I'm just going to give you the bottom line in the next screen. The Heisenberg uncertainty principle says that the range of possible positions and momenta that a particle can take on when observed are related. The uncertainty in its position times its uncertainty in its momentum must be greater than or equal to Planck's constant divided by 4 pi. And when I say uncertainty, I mean basically it's the width of this range of possible positions. The width of the peak, if you will.